In lots of the earlier lessons in this course, you and I have studied polynomials. When we were studying linear equations and their graphs, we were studying polynomials. And when we were studying quadratic equations and their graphs, we were also studying polynomials. So what I'd like to do today is talk more about what a polynomial is and what we know about the family of polynomials in general. So we should start by explaining what a polynomial is. In the process, I want us to also understand what a polynomial is not. So let's start with a working definition of a polynomial and use it in some examples. Here's a somewhat technical sounding definition. Just bear with me. We'll flesh it out a bit in just a moment. A polynomial with the variable x is an expression of the form a sub 0 plus a sub 1 times x plus a sub 2 times x squared plus ... a sub n times x to the n, where each of the numbers a sub 0, a sub 1, a sub 2, all the way up to the a sub n are all just numbers. They could be positive, they could be negative, and some of them could even be 0. And the powers on the x's are all positive integers. And it's important that we keep in mind that those exponents, as we'll call them, the powers on the x's, must always be positive integers. Now, that definition might look a bit confusing. I mean, you might have been glazing over as I was sharing it with you, but don't do that. Let me show you some examples to try to help you see what that definition is trying to say to us. Here are some things which are polynomials. Take, for example, 5 minus 27x. Now that's a linear polynomial. Now I've written it with the constant term first and then the power x to the first afterwards. That's okay. The order in which we write the terms doesn't matter. But if I'm trying to make 5 minus 27x look like the definition I shared a few minutes ago, then the 5 would be the a sub 0 and the minus 27 would be the a sub 1. Let's look at another polynomial. 4 plus 7x minus 3x squared. If you stare at that for a minute, you realize it's also a polynomial. It's a quadratic polynomial, in fact, and you and I know tons about quadratic polynomials already. And let's look at one more polynomial. Negative 3 minus 10x plus 10x squared plus 100x to the fifth. And let me just make a quick comment about that polynomial before we move forward. I could have also written that as 100x to the fifth plus 10x squared minus 10x minus 3. It would have been the same polynomial. The powers would have just gone down instead of going up. Notice that all the powers on x are positive integers. We also have that negative 3. That's a constant. That would have been sort of like the a sub 0 in the definition. But that guy really is a polynomial. Now, before I go on, let's make lots of other comments about these polynomials because they're very, very important. First of all, some of you might have seen polynomials in the past and said to yourself, I thought we were always supposed to write polynomials with the largest power first and then all of the smaller powers later. So for example, something like 4 plus 7x minus 3x squared has to be written as negative 3x squared plus 7x plus 4. That might have been what you thought. Well, it turns out it's okay to write that polynomial in either order. In fact, we could have jumbled up the terms a whole bunch and written 7x minus 3x squared plus 4. It would have been the same polynomial. So it's okay to have those terms floating around as long as we get all the terms written down for the polynomial. Okay, so in fact, I probably will write most of my polynomials with the highest power in the front and then moving down to lower and lower powers of x later on. But I don't have to do that. All right? More importantly, when you write a polynomial in that way, the powers on the variables are going down. You can read that polynomial very quickly with the highest power in front all the way down to the lowest power at the end. And because of that, we're going to give that a special name. It's going to be called the standard form of a polynomial. And we often want to be able to find that highest power of x quickly for lots of reasons. We'll talk about that later. So the standard form of a polynomial is going to be very important. So the polynomial 5 minus 3x plus 4x squared, for example, is not in standard form, but its standard form would be 4x squared minus 3x plus 5. Same polynomial, but the latter is the standard form for that polynomial. And we're going to focus most of our attention on those standard forms. Okay, I want you to notice that it was okay to have both positive and negative coefficients, the numbers that were in front of the powers of x. It's okay for those to be positive or negative, and you might have even noticed that some of the terms even are zero, some of those numbers in the front. We're going to call those coefficients. Remember, I looked at negative 3 minus 10x plus 10x squared plus 100x to the fifth. You might have been saying, wait a minute, where's the x cubed? Or where's the x to the fourth term? They were there, it's just that their coefficients were zero. And it's okay for a coefficient to be zero. So it's all right for coefficients to be positive, it's all right for them to be negative, and it's all right for those to be zero. Now, let me make a somewhat radical comment about polynomials. I'm just sort of kidding there, but let me talk about these coefficients a little bit more. It turns out that not only can they be positive, negative, or zero, they can also be roots. They can be square roots, or radicals as we'll call them later. So for example, square root of 3 times x to the fifth minus 1/4 times x to the fourth plus 19x, that's also a perfectly good polynomial. And I've read it to you in standard form, in fact. The key to any polynomial is not about the coefficients, because they can be anything they want, basically. It's that the exponents on the variables need to be positive integers. And that's the real key when you're trying to spot whether some function that's been handed to you is a polynomial or not. Now, I want you to notice that I said in the variable x, or with the variable x, when I gave the original official definition of the word polynomial. But there's actually nothing special about x. We could use a different variable if we wanted. We could have used y or z or t or anything else. So, for example, y cubed plus 8y squared plus 2y minus 17, that's a polynomial. And t to the fifth plus t to the fourth plus t plus 1 is also a polynomial. Now, some of you might be saying, well, it looks like just about anything can be a polynomial. I mean, you've written down all sorts of things already in this lesson. I don't see that there would be anything that's not a polynomial. Well, there are lots of functions which are not polynomials. And it's very important, in fact, that we be able to spot some of these functions or some of these expressions which are not polynomials. So let me now spend a few moments talking with you about some examples of expressions which are not polynomial. Here's the first one I want to look at. X to the 1/3 plus x plus 2. That is not a polynomial. Do you know why? Well, look at the exponents. It's always important to look at the powers on the x's. And in this case, I've given you x to the 1/3. Once you have a power which is not a positive integer, and 1/3 is not a positive integer, then that expression, x to the 1/3 plus x plus 2, cannot be a polynomial. So fractions for powers, they're no good if you want something like a polynomial. And also, if you think about it, square root of x can't be a polynomial then, because the square root of x is x raised to the 1/2 power. And 1/2 is not a positive integer. So something like square root of x is also not a polynomial. Okay, let's look at some other examples which are not polynomials. Take something like x to the -2 minus 3 times x to the -1. Well, the -3 as a coefficient in front of the x to the -1 is not a problem. And of course, -2 and -1 are integers, so that's good. But they're negative. They're not positive integers. And because of that, x to the -2 minus 3 times x to the -1 is not a polynomial. All right, let's look at another example. Take something like x squared plus 2x all divided by x to the 3rd power plus 1. Now, if you look at x squared plus 2x by itself, that's a polynomial. And the x to the third power plus 1, which is in the denominator here, that's also a polynomial. But when you take the ratio of two polynomials, most of the time, almost always, that expression as a whole is no longer a polynomial. And in this particular case, it's definitely not a polynomial. So something like polynomial divided by another polynomial is almost always not going to be a polynomial. So do you think you've got it? Do you think you see the difference now between what is a polynomial and what isn't? Well, let me suggest we take a quick quiz, and I'm going to ask you to do the following. Figure out which of the following expressions is a polynomial. A, x squared plus 2x plus 3x to the negative 1 power minus 16, or B, 3x squared minus the square root of x plus 3, or C, square root of 17 times x squared minus pi times x plus x to the 37th power minus 5/3, or D, 32 divided by x minus 7. If you picked C, you got it right. Even though it looks pretty weird with all of those coefficients floating around and some pretty large exponents and so on, the key to seeing that C was the answer is that all of the exponents are positive integers. And that's all you really have to check when you're looking for a polynomial. So once you start to think about this definition and you see all of these examples, you see that a polynomial is a pretty particular thing. It has to be very, very special. It's not just any ordinary algebraic expression that you throw on a piece of paper. And because of that, because we're going to be kind of picky about what the definition of a polynomial is, it's going to let us say quite a few important things mathematically about polynomials. Now, before we move forward, we need to mention some other very important vocabulary terms. So the first is what's called the degree. The degree of a polynomial is the largest power on the variable that's in the polynomial. So for example, take the polynomial 14 times x to the fifth plus 23x to the fourth minus 102 times x plus 19. The degree of that is 5 because that's the largest exponent on any of the powers of x. Notice that you have to be careful when you're finding the degree, because if the polynomial is not written in standard form, then the degree might actually be hiding somewhere inside one of the middle terms, if you will, of that polynomial. So let's try a quick quiz again. Can you find the degree of the following polynomials? Stop the video. When you think you know the answers, start it again. Let me share those polynomials with you. First, 1 plus 3x plus 4x squared minus 8x cubed. And secondly, 2 minus 10x plus 8x to the fourth power minus 5 times x squared. The degree of the polynomial, the first one I gave you, is 3, and the degree of the second polynomial is 4. Did you notice that term, x to the fourth, that was sort of in the middle of that polynomial? That gives that polynomial degree 4. If you got both of those answers right, you're doing great. Now, just keep in mind, as you keep moving through these kinds of examples, that the order on the terms of a polynomial is not what matters, and that degree might actually be hiding somewhere in the middle. Actually, knowing the degree is extremely important when you're ready to start graphing polynomials and you're trying to do other things with polynomials. And it's wanting to find the degree quickly which makes the standard form of a polynomial so helpful. Once your polynomial is written in standard form, you can read off the degree almost immediately because that highest power on the variable is right at the beginning. It turns out that one way to classify polynomials is by their degrees. Often people want to talk about a polynomial of a certain degree. For example, polynomials of degree 1, like 7x minus 4 or 10x plus 3, those are called linear polynomials. You and I have seen those already quite a bit. Polynomials of degree 2 also have a very special name. They're called quadratic polynomials. So, 4x squared plus 2x minus 13. That's a quadratic polynomial. But there are special names for other polynomials of higher degree. For example, polynomials of degree 3 are called cubic polynomials, while polynomials of degree 4 are called quartic polynomials, and polynomials of degree 5 are called quintic polynomials. We could keep playing this sort of game of naming higher and higher degree polynomials if you want, but I say we stop here. Nevertheless, make sure you're learning linear, quadratic, cubic, quartic, and quintic polynomials. Those terms are going to be used more and more throughout the course as we try to identify what kind of polynomial we're studying. Now, there's another vocabulary term that's very common when we study polynomials, and it's called the leading coefficient. The leading coefficient is the coefficient, or just the number, which is in front of the term that contains the largest power of x. So, for example, if I take the polynomial 14x to the fifth plus 23x to the fourth minus 102x plus 19, the leading coefficient is the 14. That's the number in front of the x to the fifth. Now, let's look at two other polynomials and just see if you can spot the leading coefficients pretty quickly. Here are those two polynomials. 1 plus 3x plus 4x squared minus 8x cubed, and 2 minus 10x plus 8x to the fourth minus 5x squared. The leading coefficient of the first polynomial is negative 8, and the leading coefficient of the second polynomial is positive 8. If you got those right, you should give yourself a pat on the back, because again, I was trying to hide those just a bit from you. So once you see the degree and you see those leading coefficients, the leading coefficient of each polynomial being the number in front of the power, the highest power on x, you'll be very, very well off when we're ready to start graphing in just a second. Now, I mentioned a few moments ago that one way to classify polynomials is by their degree, and we talked about linear and quadratic and cubic and so on. But there's a second way of classifying polynomials, and that's by the number of terms that they have. There are also fancy names for these, at least for a few types. So, for example, 3x squared is called a monomial because it only has one term. Think of the prefix mono, which normally means one. So think of a monomial as a one-term polynomial. In a similar way, the two-term polynomials are called binomials, and the three-term polynomials are called trinomials. So something like x squared minus 5x plus 2 is a trinomial. There's really no common name for polynomials with 4 or more terms, so I'm not going to try to keep pushing in that direction. But just make sure you have this idea down, because it's very important that we know how to classify these polynomials not only by degree, but by their number of terms. So with the goal of making sure we've got that down at least a bit, let's try classifying the following polynomial. 5x cubed minus 1, and I'd like us to classify it by degree and by number of terms. Well, the polynomial has degree 3. That's pretty quick, so it's a cubic polynomial, and it also has two terms in it, so it's a binomial. So you could say that it's a cubic binomial. All right, let's try classifying one more. X to the fourth minus 1/3 x plus 2/9. And I'd like you to try to classify that by degree and by number of terms. And I'll give you some choices. Maybe that's a quadratic trinomial, or a cubic binomial, a cubic polynomial, or a quartic trinomial. You try. Well, the answer there is the last one, the quartic trinomial. It has degree 4, so it's quartic, and it has three terms, so it's a trinomial. So we would call that a quartic trinomial. Now, one of the big reasons we care about polynomials is that they provide us with a great way to build useful mathematical functions. For example, if the radius of a circle was called x, then the area of that circle can be defined as the function a of x equals pi times x squared. And that's a quadratic monomial, right? But now you could treat that as a function. What what do I mean by that? Well, if I came to you the next day and I asked for the area of the circle, which has radius 13 feet, you could tell me by evaluating the function a of x at the number x equals 13. Or to say it in slightly less fancy language, you could just plug 13 in for x in the function a of x equals pi x squared and tell me what the area will be. If a of x is pi x squared, pi times x squared, then a of 13 is pi times 13 squared, which is just pi times 169. And if we use an approximation for pi like 3.14, then we can get a pretty decent approximation for this area. A of 13 is about 3.14 times 169, which is about 530.66 square feet. Now, why might that be helpful? Well, if I'm building an above-ground pool that is circular and has a radius of 13 feet, then I know the footprint of that pool, the amount of area it's going to take up in my back lawn. It's going to take up about 530.66 square feet. And that means I need to get enough sand to put under that pool to make sure the footing is nice and soft while I walk on my pool to cover at least 530 square feet. But this function a of x is even more helpful than this. Why? Well, maybe my kids come to me later that night and they say, Dad, we saw an even bigger pool on TV today, and it's also circular, but it has a radius of 21 feet. Could we buy that one instead? Now, I actually have 1,000 square feet that I could use for this pool in my back lawn. Now, maybe you and I could work together to figure out if this bigger pool is going to fit. Let's try using that function a of x, remember it's pi times x squared, and see if this pool will actually fit. Why don't you think about this for a moment? After we talk it through a bit, you might want to stop the video and see if you can finish the problem. Here's what we have so far. A of x is pi x squared, so a of 13 is pi times 13 squared, which was pi times 169, and using 3.1 as an approximation for pi, I saw that that was 530.66 square feet. What would I do if the pool has radius 21 feet? Try to see if you can determine what the area is going to be that's going to be taken up. Well, does it fit? If I want that area of the footprint to be no more than 1,000 square feet, I can go back, take a of x, and plug in the new radius, 21 feet, and see if I get the area that I want. Well, a of 21 is pi times 21 squared, which is pi times 441. And if I use 3.14 again as an approximation for pi, and I multiply that by 441, I'm going to get 1,384.74 square feet. Unfortunately, I don't have that much square footage in the back. I only had 1,000 square feet. So I have to go back to my kids and say, sorry, we can't get that bigger pool. We can't go from a radius of 13 feet to a radius of 21 feet because we got a much larger area than the one that we really have available to us. Now, the point here is that the function a of x equals pi x squared is extremely helpful because if I wanted, I could now try several other values of x for the radius of this pool, and I could see if I could get a slightly larger pool, maybe bigger than 13-foot radius, but smaller than a 21-foot radius, to see if I could fit that pool in. So this function is very helpful as I try to evaluate this area for several values of x. Now, I'd like to look at a few more examples of evaluating polynomial functions. And evaluating simply means plugging numbers in and seeing what you get as an output. So let's try the following, and you might want to try it yourself just to see how you do with evaluating functions. Here's the problem. Determine f of 0, f of 1, f of 2, and f of negative 1 for the function f of x equals 2x to the fourth minus 3x plus 5. Well, what did you get? Let's see how everything worked out. F of 0 equals 2 times 0 to the fourth minus 3 times 0 plus 5. And now you have to do order of operations. So I need to do that 0 to the fourth first. But that, of course, is just 0. So f of 0 really is 2 times 0 minus 0 plus 5, which is 0 minus 0 plus 5, which is just 5. So f of 0 is 5. We've just evaluated the function f of x at x equals 0. What about f of 1? Well, it's 2 times 1 to the 4th minus 3 times 1 plus 5, which is 2 times 1 minus 3 times 1 plus 5, or 2 minus 3 plus 5, which is 4. So f of 1 is 4. How about f of 2? F of 2 is 2 times 2 to the 4th minus 3 times 2 plus 5. We must do that exponent first, and we'll have 2 times 16 minus 3 times 2 plus 5, which is 32 minus 6 plus 5, which is 31 once you do all of the subtraction and addition. So f of 2 is 31. And lastly, f of negative 1 is 2 times negative 1 to the 4th minus 3 times negative 1 plus 5. Negative 1 to the 4th is actually positive 1. The power of 4 will cancel out the negatives because negative 1 to the 4th is negative 1 times negative 1 times negative 1 times negative 1. And so we have 2 times positive 1 minus 3 times a negative 1 plus 5, which is 2 plus 3 plus 5, or 10. So f of negative 1 equals 10. Now, before we look at one more example of evaluating a polynomial, let me point out a very practical reason why it's useful to be able to do such an example. We just showed that f of 0 equals 5 just a moment ago. And that means that the graph of f of x equals 2x to the 4th minus 3x plus 5 must go through the point 0, 5. 0 was the x value we plugged in, and 5 was the y value that came out. So that means the graph must go through the point 0, 5. And now we know that it also goes through 1, 4, and 2, 31, and negative 1, 10, given the information that we just built a moment ago. And one of the best ways to sketch the graph of a function is just to plot a bunch of the points. We just found 4 points, in fact, in that example, and then just connect the dots. So evaluating a polynomial function quickly at several values of x can be very, very helpful when we're trying to visualize the graph of a function. Now, here's one with a little bit of a twist in it. So I'm going to ask you to try it first. You might want to grab a pencil. You might want to stop the video once I share the example with you. Try it yourself, and then we'll go from there. Here's the example. Evaluate g of x equals x cubed minus 4x at the values x equals negative 2, x equals 0, and x equals 2. Now, if you tried that on your own, you might be scratching your head a bit. Let me walk through it with you just in case you are. Maybe you're not. Maybe you're fine, and we'll see what these values are. But let's see what we get. G at negative 2, or g of negative 2, is equal to negative 2 cubed minus 4 times negative 2. And that's the same as negative 8, because that's negative 2 times negative 2 times negative 2, minus 4 times negative 2, which is the same as negative 8 plus 8, which is 0. So what I'm really seeing here is that the point negative 2, 0 is on this graph, or the graph goes through that point. That's an x-intercept of this graph because the y value equals 0. Okay, let's now evaluate g at the value x equals 0. G of 0 is 0 cubed minus 4 times 0, which is 0 minus 0, which is 0. Well, wait a minute, that gives me a second x-intercept then. It's right at the origin, 0, 0. Now let's plug in 2. Let's evaluate g at the value x equals positive 2. And you'll have g of 2 equals 2 cubed minus 4 times 2, which is 8 minus 4 times 2, which is 8 minus 8, which is 0. Now wait a minute, that's a third x-intercept. It's at the value 2, 0, or at the point 2, 0. Could that be correct? Could the graph of g really have those 3 x-intercepts? Well, in fact, if you stare at a sketch of that graph, you'll see that g of x really crosses the x-axis at x equals negative 2, x equals 0, and x equals 2. Our calculations were actually correct. But this now reminds me of some of the language we brought up several lessons ago, which was related to functions. Remember how we talked about the domain of a function and the range of a function? The domain was a set of legal inputs, and the range is a set of outputs for a function. What can we say about the domain and range of a polynomial of any kind? Well, actually we can say a whole lot. First of all, no matter what polynomial function you're studying, it turns out that the domain is always the set of all real numbers. In other words, there are no illegal values of x to plug in to a polynomial. What can we say about the range? Well, it turns out that the range of a polynomial actually depends on something. It depends on the degree of the polynomial. If the function's degree is odd, then it turns out the range is all real numbers. Go back and look at the graph of g of x that we just looked at a moment ago. Notice that one branch goes upwards forever and the other branch goes downwards forever. And that tells us that the range is actually the set of all real numbers. And this is always going to be true of a polynomial with odd degree. If the polynomial has an even degree, then something different happens. Either both branches go up or they both go down. And because of this, there's going to be a piece of the range that's actually missing, so to speak. The range will not be the set of all real numbers. So when the degree of a polynomial is even, we're going to have a range that's some portion of the set of all real numbers. Maybe something like -1 to infinity, or 3 to infinity, or -infinity to 2, or something along these lines. Well, today we've talked about polynomials in general, and we've introduced a whole bunch of vocabulary terms about polynomials. I hope you'll review those as we go on, or before you go on, really, because I'm going to use those vocabulary terms in the future. Next time we'll talk about the graphical side of polynomials and discuss a variety of examples there.